So, hi everyone. So it's a pleasure to have with us today Dor Elboim, working with Alex Live, Patrick is here, who will tell us about five-dimensional cycles. Yeah, just okay. Right.
Okay, thank you very much, Omer, and thanks for the invitation, and thank you all for coming. So today I will talk about the interchange process, and this is a process of random permutations obtained by randomly composing transpositions along edges of a graph. And this is a joint work with LSR. Okay, so let's start with the rigorous definition of the model. So you have a graph, G, and it can be either finite or infinite. And on each vertex of the graph, there is a particle, distinguished particle. And on each one of the edges, you have an independent Poisson clock. So this is just a clock that runs at random times. If you want the process up to time beta, then it's going to be around beta. And actually including Poisson beta many times. And okay, so now what is the process? So it's very simple. On each one of, every time an edge E, which is UV, rings, the two particles on U and V switch. So the particle on U jumps to V and the particle on V jumps to V. And right, and then you do it up to time beta, and then you get a random permutation, pi beta, from the vertex set to itself. This is the random permutation to tell you for each particle where it ended up at the time beta. Let's have some example. So you have, let's say, this C-squared graph, and then you have particles on the vertices, and let's say they have different colors so that we can follow them. And then you start running the process and edges start to randomly. So let's say this edge rings, which means that these two particles switch like that. Now this edge rings and these two particles switch. Right, so the yellow particle started in here, moved there, then there, and it keeps going. So they keep switch like that randomly. By the way, if the graph is finite, then it's just like choosing a uniform random edge and switch. And at time beta, you get a random permutation, so an arrow indicates that the blue particle that started over here ended up over there. So this is the permutation. Fine. And one thing that you can do is follow the cycle structure of the random permutation. So this red particle started in here and ended in here, so it's a fixed point. And then in here you have a longer cycle, so you have a cycle of length 5 in the permutation. Write any permutation from both cycles. And I think a basic question I will try to motivate later in the talk is whether all these cycles necessarily close. Maybe they never close. Maybe you just see this infinite two-sided trajectory that never close. Okay. So before that, let me tell you a little bit about the history and the previous works. So I think the first result is by Diaconis and Shoshani. They studied the interchange process on the complete graph around 40 years ago. And then on the complete graph, it has a simple interpretation as mixing a deck of cards. So you just have n cards. And each time you choose two cards uniformly at random and switch them like that. Right? Because you are doing the interchange process on the complete graph, which means that you can switch any two particles. So it's like cards. You choose two cards uniformly at random and switch. And the question is how long it's going to take for the deck of cards to mix, where mixed means that the random permutation that you get is close to the uniform distribution. And then they prove that it's going to mix in half n log n time after half n log n random transpositions. And they used the representation theory to do it. Yeah, so it's a pretty important result. They show that also that there is a cutoff at half n log n, which is one of the first examples of the cutoff phenomena. Right, and then since this result, there are people studied it on many graphs. And one notable result is the proof of Aldous conjecture by Caputo, Liggett, Richthammer. So they show that for any finite graph, if you do the interchange process on the graph, the spectral gap of the interchange process is equal to the spectral gap of the simple random walk on the graph. Which means that in some sense, if you want to understand the mixing time of the interchange, it suffices to understand the mixing of the simple random walk on the graph. So this is Aldous conjecture. Right, so this is one side of the story, and the other side is the cycle structure. So this was initiated by Balin-Todt. The laser is broken. This was initiated by Balin-Todt and independently by Eisenman and Nachtergaele, who observed the connection between node cycles in the interchange process and spontaneous magnetization in the quantum Heisenberg format. I won't tell you what it is, but I'll just say that it's a well-studied model of statistical physics. And it's a quantum version of the classical Heisenberg model, you know. And in particular, Todt made the following conjecture, which is around 30 years ago. It's called Todt conjecture. And it says that if you are doing the interchange process on CD, then it depends on which dimension you are. So in dimension 2, no matter how long you're going to run the process, you will always have only finite cycles in the permutation. And in dimension D or larger, you're going to have a phase transition. So you have a critical time, beta C, such that if you run the process for beta which is smaller than beta C, then it's like 2-dimension, almost surely all the cycles will be finite. And if you run it for more than the critical time beta C, then almost surely you will see it in the two-sided project. So that's the conjecture. Is this clear? And it sort of corresponds to an expected phase transition in the quantum Heisenberg format, but it's not exact. Okay, and since the work of Todt, there are many results on the cycle structure of the interchange permutation. One result is by Alon and Kozma. They used the representation theory to find an exact formula for the probability that the permutation is one giant cycle. But this probability is pretty small. And what you really want to show is the existence, the emergence of long cycles. So if so this is for general finite graph. Right. So you want to show that with high probability you will have long cycles. And so in infinite graphs you want to show infinite cycles, and finite graphs you want to show macroscopic cycles. Okay, so right, you have many results on the emergence of long cycles. On the complete graph, you have results of the sticky duet, Schramm, Kozma. So here they show that you have linear cycle, and Schramm then improved it to show that you actually have convergence to the so-called Poisson-Dirichlet distribution. I won't tell you what it is. Then you have another proof using the representation theory. Gadi Kozma likes to study this theory of representation. And then you have the results on trees by Roman Angel and by Ellen Hammond. And some results on the hypercube and on Hamming graphs. This is like the product of two complete graphs. And also a recent result on random regular graphs. So as you see, it's pretty active over the last couple of years, but still no similar results for CD. And in particular, no progress toward the original conjecture.
Dor, a question?
Yes.
Does long quote unquote long cycles? Does this have a universal meaning, like much longer than an average or something? What?
So on finite graphs, when I say long cycles, I mean cycles that capture a fraction of the vertices.
Yeah.
Like cycles. And on infinite graphs, usually I mean just infinite cycles.
Oh, okay. All right. Thanks.
Thank you. Are there any other questions? Right, so here is the result that we proved. So this is a month ago. Now it's on the archive. So if you do the interchange process on CT, when the dimension is at least 5, and you run the process for sufficiently long amount of time, remember, beta tells you how much each edge rings on average. So each edge rings approximately beta times. Then almost surely we'll see these infinite cycles in the permutation. Right, so in 2 dimensions, the conjecture is that the cycles will always close, but we proved that in 5 dimensions, almost surely you will have this infinite trajectory that never close. Okay, are there any questions about the model or the result? Yeah.
What dependence of beta on D?
Okay, so it's a bit related to the percolation. It's something that I'm about to explain. The conjecture is that beta should behave like 1 over D, asymptotically in the dimension. But we get from the proof, we didn't try to optimize this, but we get something pretty bad. I don't know, e to the D or e to the million D or. Right, thank you.
Is it known that if that can be just one transition from finite cycle solution to the infinite solution?
Okay, good question. Yes, it's not, you don't have some simple monotonicity in this model. It's possible that you run the process, you have finite cycles, then infinite, then finite, you run it for a bit longer. You get finite cycles again, then infinite again. But it's conjecture to have a critical value. So indeed, in here, we don't know how to rule out that you have a couple of phase transitions. But one thing that is very easy to show, it was well known before the work, was that in all dimensions, if you run it for a sufficiently short amount of time, then you will have only finite cycles. And why is that? Because remember, each edge rings approximately beta times. So if beta is very small, almost none of the edges ring. So it's sort of a percolation argument. What you do, you consider the set of edges that ring at least once. So here is the set of edges. And then you know that this set is a percolation with parameter 1 minus e to the minus beta, like the probability that an exponential is less than beta. And if this is less than the critical probability of percolation on CD, then of course the components are finite, and then the cycles of the permutation contain cycle connected components. Right, but now you want to show that, by the way, it is still open to show that in dimension 2, for all beta, you will have only finite cycles. So this is still open. And maybe it's a good opportunity to mention some other open problems. So, right, of course, the conjecture is starting from dimension 3. We only have it for dimension 5. We have some partial results in dimension 4, and in dimension 3, we have nothing. So this is still open. Also in dimension 4, we can't quite get the infinite cycles result. And as you asked, indeed, there is still the problem of showing that you have a critical time, such that before you have finite cycle, after that you have infinite cycle. Another question is doing it in finite volume, like on a finite box. And then the conjecture is that the cycles will be linear, will capture a fraction of the vertices, and will converge to the Poisson-Dirichlet distribution, like the result of Schramm on the complete graph. So this is still open, and of course you have the quantum Heisenberg for magnet. This is not exactly the interchange. You add another factor to the number of cycles, which makes everything much more complicated. And okay, I didn't say it, but the way you analyze this is you interpret this cycle as some sort of a random walk. So it turns out that when you start following the cycle, exposing the cycle to permutation, it behaves like a random walk. And this is why you expect the conjecture is true, because you know that the random walk in 3 dimensions will be transient, and in 2 dimensions it will be recurrent. So if you knew that it behaves like a random walk, you would prove the projection. Right, and this is what you do. It turns out that the cycle is a self-interacting random walk, and this is what we do in the proof. We analyze this self-interacting random walk. And since our proof is somewhat combinatorial, and it doesn't use the exact local interactions of the interchange, we expect that you can use it to analyze other self-interacting random walks. There are many such walks in the literature. Okay. Right, so now I want to explain this self-interacting random walk. This is called the cyclic random walk. So what is the cyclic random walk? What you want to do, you want to analyze the cycle of the origin in the interchange. So forget about all the particles, except for the particle in the origin. This particle is just doing a simple random walk, right? Because each one of these edges will equal to origin. So it's just doing its random walk, simple random walk. But you want to understand the cycle of the origin. So let's say it ended up here at time beta. So now we want to understand the particle, the red particle, started here at time 0. And you also want it, and it is also doing the random walk. And so on. And let's say it ended up over here at time beta. So now you have the green particle started over there at time 0. And you concatenate these random walks, and you got a bigger random walk. So why is that not a proof of the conjecture? Why is that not just a random walk, just a single random walk?
Some information about the blocks I do.
That's right. So each particle is a single random walk, but they are not independent. Right? Imagine that the first particle started over here, it does its random walk thing, it arrived over here. No, we should not it's doing its random walk, arrives over here at time beta over 2, and then jumps along this edge and continue up to here at time beta. Is that a different color? No. Anyway, now you consider the particle that started over here at time 0, right? And it's also doing its random walk thing. And then let's say it arrived over here exactly at time beta over 2 minus epsilon. So now you know that the particle that was here jumped along this edge over there at time beta over 2. So you know that there was a switch along this edge. So you know that now this particle is forced to jump over there because there was a switch along this edge, right? So now the second random walk is no longer doing an independent random walk. It's doing an independent random walk until it arrives into this place, and then it is forced to jump. And it goes both ways. So it can be forced to jump, and it can be forced not to jump, because let's say this is the random walk, the first one, and it was here at time beta over 2. And then you have the second random walk that arrived over here at time beta over 2 minus epsilon. And then it attempted to jump over here at time beta, let's say beta over 2 minus beta over 2. In that case, it cannot jump over here, right? Because it's like a different particle. You have a different particle over here. And you know that this particle did not jump up. So you know that it is forced not to jump. So these are the rules. This is called the cyclic random walk. Cyclic random walk is just the walk that goes along the first particle, the blue particle, between time 0 and beta, then along the red particle between beta and 2 beta, and so on. And it has these kind of interactions. Is that clear? You sort of go along a simple random walk until you are forced to jump or forced not to jump when you hit your history. So this is the cyclic random walk. People like to have, okay, so we say that the walk interact with its past in time t if there exists some integer k such that the distance between the walk at time t, w will be the cyclic walk. If the distance between the walk at time t and the walk at time t minus an integer multiple of beta is a distance at least 1. Because, right, when you go backward in time, an integer multiple of beta, you are like at the same interchange of environment when you go along the cyclic walk. So sort of here you go beta over 2 times backward, you go beta time backward in time along the cyclic walk, and it's like a different particle. Okay, and as we said, so W evolves like a simple random walk as long as it doesn't interact with its past. And right, last thing to note is that if you close the cycle, so if you return to the origin at an integer multiple of beta, then you're just stuck in a loop. Right, you will just, if you return over here at the right time, you will just keep being forced by your history to go along the cycles again and again until infinity. And it means, so in the interchange process, it means that you close the cycle. And the cyclic walk will just keep going like that. Okay, so people like to have this kind of space-time picture. So here you have just a one-dimensional graph, just a t, and here you have time, and you run the interchange process for time beta, and then these red bars indicate the rings along the edges. So this edge rang at the right time, so this is the interchange environment, so you know exactly what is the random permutation. You know that you have here a cycle of length 2 position, and here you have a more complicated cycle. So now, suppose you want to understand the cyclic random walk starting from the origin. What do? You just copy the same environment up in time. So you just take the same environment and put it on top of the old environment, and you keep doing it until infinity, like that. Just copy the same environment periodic with period beta. This is why it's called the cyclic random walk. And then what is the cyclic walk? So it's just a walk that starts from the origin, and every time it hits the red bar, it crosses to the other side. So this is the cyclic random walk. And so here you know that the cycle of the origin is of length 3, because you return to the origin at cyclic time, the time 3 then. Right, is it clear that cyclic random walk? Are there any questions? So as you see, you don't really need to understand, you don't really need all the randomness of the Poisson blocks along these edges. You just need to expose the Poisson blocks along the cyclic random walk in order to know its trajectory. So let's say you want to sample the cyclic random walk using a computer simulation, let's say. You don't really have to sample all of the interchange environment. In fact, you only need the randomness of a simple continuous time random walk in order to sample the cyclic walk. That's exactly what we said over here. You take the same step as the random walk, unless you're forced to do something else, and then you do it. Right. So this will be called the driving random walk. So this is the cyclic walk derived by a simple continuous time random walk. Okay, so this is the cyclic walk, and now the idea is to analyze that, and I will try to tell you the main ideas in the proof of how to analyze this walk. Okay, so right. So it is known that the higher the dimension is, the less intersection a simple random walk will have with itself. And remember that in here, so every time you intersect your past, you interact with it. And so the less intersection you have with your past, you expect it to be easier. Because the cyclic walk will behave more like a simple random walk. So in some sense, this is the idea of the proof. So you have the following cyclic argument. So first you show that the cyclic walk behaves like a random walk. Then you know that at least in high dimension, the random walk will not intersect itself much. And then it means that the cyclic walk will not intersect itself much. And which means that the cyclic walk behaves like a random walk. So now, how to make a proof out of something like that? You use induction, right? So you show that on shorter time intervals, the cyclic walk behaves like a random walk. Then you show that on longer time intervals, it won't intersect itself much. And then it means that on longer time intervals, it behaves like a simple random walk. So that's the idea. You want to show that the cyclic walk behaves like a random walk. And then you prove the conjecture, because you know that the random walk will not return to the origin with positive proof. Okay, so let's try to do this induction. So the induction base is very easy, because we know that the cyclic walk up to time beta is just a simple random walk, because it's just the first particle, just the particle starting from the origin. So up to time beta, it's exactly random. Of course, I didn't tell you what is behaves like a random walk, what it means. And of course, you have a series of inductive assumptions that you want to prove. But let's not get into that right now. So now, what you do is suppose it behaves like a random walk up to time beta to the k, let's say, and you prove that it behaves like a random walk up to time beta to the k plus 1. But how do you do it? Like, suppose you have some information on shorter time interval. How do you infer info? How do you get from that information on longer time intervals? And the idea is pretty simple. So you just use concatenation. What you do, you take independent cyclic walks and you run them up to time beta to the k. And you know, by the inductive assumption, you know that each one of these walks behave like a simple random walk. That's the inductive assumption. And then what you do, you just put them like that, one on top of the other. And this will be the concatenation of these walks. W1 up to W beta are the independent cyclic walks of length beta to the k. You concatenate them. And you get a certain walk of length beta to the k plus 1, right? But of course, this is not a cyclic random walk, because in here you forgot about interactions between different parts of the walk, right? So if the red path intersects the blue path, then when you take the concatenation of independent walks, you don't have to take it into account. But for the long cyclic walk, you have to take this kind of interaction into account. But turns out what you want to do is to couple. You want to try to couple the concatenation of shorter walks with a long walk of length beta to the k, with a long cyclic walk of length beta to the k plus 1. So this is the idea. You want to show that with very high probability they are really close. Is it clear? Yeah.
So these things have similar lengths to something a little bit different than beta to the k plus 1. Like, isn't it like beta to the k plus 1 minus 1 over beta minus 1 or something?
Because beta is not an integer.
Oh, okay.
Let's say beta is an integer for now. So you take beta independent walks of length beta to the k plus 1. You concatenate them.
Oh,
get
okay, sure. Right.
some walk of length beta to the k plus 1.
Right. What sense very close?
I don't want to get into that. But basically, with really high probability, super polynomial data, like up to a small polynomial level. polynomial in the length. Let's say the length to the. No, just the entire trajectory is close up to some polynomial, up to like the length to the power of 0.01. Right, so if the idea clear, you just take these independent cyclic walks. You know that each one of them behaves like a random walk. You concatenate them, so they are independent. You know that the concatenation behaves like a random walk. And then if you know that the long walk behaves like the concatenation, then it means that the long walk behaves like the random walk.
So you don't need to take any overlap between them, because it feels like at the point that you concatenate, you change something. The independent case compared to the.
That's right. So this is exactly where you use 5 dimensions. So when you take these two walks and concatenate them like that, then it is well known. It is a well known fact that if you have two simple independent walks in 5 dimensions, then with positive probability they will not intersect. They will be completely disjoint. And then the concatenation works well. But sometimes it doesn't happen. And this is what creates the error. You want to show that the error is not big. But this, of course, doesn't work exactly as it is because what happens if one of the paths closes? So you have these shorter walks. So remember, it's a cyclic walk. So if it closes, then it just keeps going in a loop. And then, of course, the coupling fails because so this is the concatenation of independent walks, and this is the long walk. So of course you cannot close the cycle here because it's a permutation. You have to close it in the beginning. So you just keep going sort of independently, and the coupling fails really bad. So one thing that you can try to do is to say, okay, let's say that let's condition on the shorter walk not to close, but it's not a good idea because you lose the entire Markov property. But it turns out that the natural thing to do is to consider a regenerated cyclic walk. Okay? So what is a regenerated cyclic walk? It's just a cyclic walk that restarts independently every time it closes. So it turns out this is the natural thing to do in this case, but we didn't understand this at the beginning. So you have this cyclic walk. If you close it at a cyclic time, at an integer multiple of beta, you just forget about it and it restarts independently. And then you can show that then the coupling works. So here you have the red walk that closes and then restarts independently. And now these two walks, it turns out you can show that they are close with high probability. Right, but something is missing in this. And so what we did so far is to say, let's assume that each one of the pieces behaves like a random walk. So let's say it behaves like a random walk everywhere. It's sort of independent, so the entire thing looks like a random walk. But then, of course, sometimes it doesn't behave like a random walk because sometimes it is entangled in its history in a very complicated way that makes it keep being forced to do all kinds of stuff, and it doesn't behave like a random walk anymore. So the question is what to do with this kind of situations. And for that, so this is the escape algorithm. This is probably the main idea. So just the concatenation gives you some bound on the length of the cycle, but it doesn't really show that you go all the way to infinity. Right, so we have to be able to deal with local catastrophes. What do I mean by that? So suppose the cyclic walk went for a long way, and then it created this kind of a mess in here. So let's say it's square of beta by beta, where the walk is completely space-filling. So this happens with positive probability. If you want to go to infinity, eventually it will happen, right? So in here, it doesn't look like a random walk at all because it keeps being forced to do all kinds of things. So it's not a random walk. And okay, so one thing you can say, let's wait until you exit this mess, and then it behaves like a random walk again. But what happens if you exit and then return, and then create a bigger mess? And maybe it keeps going until it swallows the origin, and close the cycle. So it sounds a bit silly, but it's really something that you have to worry about. Maybe it happens to be the case that all the cycles are finite because you created this little mess that grow until it swallow the origin and close the cycle. Right. So I don't want to define what a mess is, but suppose you created a certain mess of silent scale. What you want to do is to be able to escape from it fast before making a bigger mess. And here is the idea. So you take a smaller scale. Let's say a polylogarithmic scale. M is log L to the 4. L is the size of the mess. And you cover everything around the mess with little blocks of side length M. And then what you want to show is that with really high probability, all of these little squares are escapable. What does it mean to be escapable? It means that there is a cyclic walk that starts from within one of these and escapes far. And you want to show that all of them are escapable with high probability. Okay, let's define what is escapable. So you want to zoom into one of these little green blocks. And this is what it means to be escapable. So you take root m, let's say this is log L to the 4. You take root m equally spaced points inside the block. And then escapable means that one of the cyclic walks, starting from these starting points, escapes far. So escapes very fast to a distance of 10L. Remember, L is the size of the mess, so you want the cyclic walks from inside the green block to escape to a distance of at least 10, like away from the mess. Okay, so this is what it means to be escapable. And then you want to show that with really high probability it is escapable. And it makes sense, right? Because these walks are somewhat independent. So the probability that none of them escapes fast, each one of them behaves like a random walk, let's say by some inductive assumption. The probability that none of them escapes fast is like exponential in the number of points. So e to the minus root n. This is the probability that none of them escapes. And because of how we set up the parameter, this is like e to the minus log L squared. So it's still really small compared to the big scale, which means that you can union bound. So this is a really small probability. What you can do is union bound and say that with really high probability, all of them are escapable. Right? Okay. So now you know that all of these. Okay, but these walks are not exactly independent, right? Because they use the same interchange environment. But what you can do is sort of expose them one after the other. So the first one has a positive probability of escaping far because it just behaves like a random walk. We are inside some framework of an induction. So we know that these short walks behave like a random walk. So
walk up to some time is what we call fast.
yes, the first thing here will be L squared. So a random walk in time L squared, you expect to get to a distance of 10.
So this is a square length function.
Yes. So now what you show is that each time conditioning on the previous walks, you have a positive probability of both escaping fast and also not hitting the previous one. So sort of conditioning, every time conditioning on the previous walk, on the previous walks, you have a positive chance of escaping and not hitting the previous one. And this shows that indeed the probability that none of them escapes is exponential in the number of points. Right, but why does it help you? So you know that from each one of the little blocks, there is a cyclic walk that escapes fast. By the way, remember, so in the interchange, you can start a cyclic walk from any one of the vertices. So this is what I mean. So it means that each one of these, if you start, there is a point inside this little block such that the cyclic walk escapes fast and far. Yeah, so why does it help you? Because when you're trying to leave this mess, you will enter a little green block for the first time. And then you know that one of the cyclic walks out of this little block escapes. So here is a zoom into that block. You know that one of the walks will escape. And then in here, it's just like a simple random walk inside. What's happening inside? So you know that you will have a non-negligible probability of connecting to the right point at the right time and escape. This is the idea. So right here, the cyclic walk behaves like a random. So just for a simple random walk, you have a box of silent n. Just for a simple random walk, you have a probability that is polynomial, probability at least polynomial in M of connecting to the right point at the right time and staying within this block. Just for a simple random. And if you did that, you just connected to the right point at the right time and stayed. That's the idea. But of course, this is a pretty small probability. The probability to connect exactly to the right point at the right time is pretty small. But you can try it again and again in different blocks. That's the idea. So let's say here you enter this block, you know that one of the cyclic walk escapes. You try to connect to the right point at the right time. If you were able to do that, you escaped. And if not, if it didn't work, if the escape attempt failed, then just try again and again. Just keep doing that until it works. That's the idea of the escape algorithm. And remember that each time you had m to the minus, like polynomial in m probability of escaping fast. And you have like polynomial in L many attempts. So this is like 1 over log probability. Every time you enter this small logarithmic size block, you have 1 over log L probability of escaping. And you have polynomially many attempts in L to escape. So this is the idea. Is it clear? Let's go over it once again. So what you do, you have this mess. You cover everything with little green blocks. You show that each one, with really high probability, each one of these blocks is escapable, which means that there is a cyclic walk starting from inside and escaping very fast and very far. And then what you do, you just connect your cyclic walk to the right point at the right time and escape. And if it doesn't work, you will keep doing it again and again. That's the idea. So what it shows is that before creating a mess of size, let's say twice the size, you will be able to escape to a distance of 10, like much farther. Are there any questions about the escape algorithm? Okay, and now the question is how to connect all of these ideas into a multi-state proof that actually works. So I need to tell you what are the inductive assumptions, like what it means to behave like a random walk. And so you're going to have 4 inductive assumptions. The first 2 are the global ones, and the last 2 are more local, showing that the walk is not locally too messed up. And okay, so the first 2 are just that the cyclic walk. Okay, you set it up such that Tn is 4 to the n. You assume that it behaves like random walk up to time 4 to the n. You want to show it behaves like random walk up to time 4 to the n plus 1. And then the inductive assumption, the first inductive assumption is that you have the right transition probability. So W is the cyclic walk. You want to show that the probability to end up at a particular vertex behaves like time s to the minus d over 2. This is what happens for a simple random walk. The probability to end up at a particular vertex decays like s to the minus d over 2. And then the inductive assumption is that you have this up to a certain buffer of epsilon. So it says that you have the right bound transition probability for the cyclic random walk. The second assumption is that the cyclic walk is approximately Brownian. What do I mean by that? So it is well known that a simple random walk, you can couple it with the Brownian motion. This is the KMT embedding, if you heard about it. You can couple it with the Brownian motion so that with really high probability, they are very close. So you want something similar for cyclic walk. And for simple random walk, the variance of the Brownian motion that you couple it with will be 1, but here the variance will not be exactly 1 because these local interactions will affect you a little bit. But it shows that you can couple them. So the cyclic walk and the Brownian motion are both of order Tn. So this says that with really high probability, they will be a distance Tn to the 2 over 5. By the way, so Tn is 4 to the n, n is log of t. So here it says you have like e to the minus log squared probability that they will be really close. These are the two global inductive assumptions that tells you that the cyclic walk behaves like a random walk. And now let me tell you about the two local inductive assumptions. Okay, remember that we want to try to justify this concatenation. You want to show that if you concatenate these two paths with positive probability, the future will not intersect the past. This is what you want to establish. And now the question is, so I'm going to define the notion of relaxed times. The question is, what do you need to assume? Let's say you have the past of the walk up to here. What do you need to assume about the past so that the future will not intersect it with positive probability? And it turns out the answer is that the past of the walk will not be heavy in each one of blocks around this point. So if the past of the walk does not spend too much time in each one of these bigger and bigger blocks around, then the future of the walk will have positive probability of avoiding the past. At least, of course, just in 5 dimensions. In 3 dimensions, the past and the future of the walk will intersect with high probability. But in 5 dimensions, if you assume that the past is not heavy in each one of these blocks, then it means that the future will not intersect it with positive probability. So let me define it more precisely. Okay. So a block P, X, R is just like a set of points, a distance, a nodes R or X is called heavy if, okay, so you have here a block of side length R. And suppose you have a simple random walk inside it. How much time do you expect the random walk to spend inside this block? R squared, right? If you have a block of side length R, you expect a simple random walk to spend roughly R squared time inside it. So heavy means that the cyclic walk will not spend much more than R squared time inside the block. So this is not expected. That a simple random walk will spend too much time inside the block. So the block PXR is called heavy at time T. So you want to consider the set of vertices in the block that are visited by the walk up to time T. And you want that this set of vertices is more than R to the 2.5. Okay, so a little bit more than R squared. So a block is called heavy if the cyclic walk up to time T spends visited more than R to the 2.5, many vertices inside. And then a time T called relaxed is what it means to be heavy. And the time t is relaxed if all the blocks around WT are not heavy. So if the blocks B, W, T are not heavy for all large R. Okay, this is exactly what we said. So the time t is called relaxed if all the blocks around W of t are not heavy with respect to the walk up to time t. And this is exactly what you need in order for the future to mix it with positive probability. Okay. So now what we proved is that. Okay, I will find it over there. So let's say tau t. This is the first time after t, such that Ws interacts with the past. And so you have the walk up to time t, and then you want to consider the first time after t where you interacted with your past, like that. And what we basically explained in here is the following lemma, that if t is relaxed, then you have a decent chance of not hitting your path for a long time. And then the probability that tau t is larger than t plus 4 to the n minus 1, given everything up to time t, is at least 1/2. Right, so, okay, what you show, so a time is relaxed if the path is not heavy with respect, and if all these blocks around WT are not heavy with respect to the path, and then this lemma tells you that then there is a positive chance that the future will not meet the path. And it means that you can couple it with an independent walk, you can couple it with an independent cyclic walk that just starts from time 0 over here. So this is what it means that you have a relaxed time. This is what it means that the time is relaxed, and it's important for the concatenation. So in order to justify the concatenation, you exactly need this relaxed time. And of course, you cannot ensure that all the times are relaxed because maybe the walk is sort of messed up locally like that. But what you can show is that 90% of the time are relaxed. So this is the inductive assumption. It tells you that with really high probability, at least 90% of time are relaxed. And okay, the last inductive assumption, forget about what is written in here, but it sort of tells you, so far we said that the cyclic walk behaves like a random walk. So in this, we say that a pair of cyclic walks starting from a pair of vertices in the grid will behave like a pair of independent random walk in the sense that most of the time, the second walk will be far from the entire trajectory of the first. So this is the pair of that we use. Forget about the exact bounds that you have in here. And this is important in order to locally avoid your path. So somehow, if you enter a certain block a couple of times, this pair property allows you to locally avoid your path. Right. Okay, I see that I'm almost out of time, but maybe I will just tell you about the last idea, which is a certain multi-scale improvement. So the question is the following. You have a bunch of inductive assumptions that hold with really high probability. But the longer the walk, you need better and better probability. right? So this is the failure probability bound into the minus n squared. So when n is larger, when the walk is larger, you want better and better probability bound. So the question is, how can you use the inductive assumption in order to prove the inductive step? Like, how can you get this better and better probability bound? That's the question. Is it clear? You want bigger scale, you want better probability bounds. So, but the inductive assumption only works with smaller probability. So how can you use it? And the idea is that to use the independence, the spatial independence. The idea is pretty simple. What you do, you split the grid into a lot of small blocks, like that. And a block is called good if all the inductive assumption holds for all paths inside the block. So here you have a block. It's called good if all these cyclic walks starting from inside the block satisfy the inductive assumption. And what you show is that with really high probability, you don't have a lot of bad blocks. So this is how you get the improvement. So you take split it into a lot of small, let's say polynomially small, 10 to the 0.01 little blocks like that. And each one of the blocks, the probability that it's bad is small, but not that small. But since these joint blocks are independent, it means that with really high probability, you won't have many bad blocks. That's the idea. So with really high probability, you won't have more than constantly many bad blocks. Okay, I see that I should finish. I will just say that you have two key estimates that I won't have time to prove. The first one is that you don't see these big heavy blocks. And the second one is that is to find these relaxed times, these times in which you have a positive probability of escaping and never hitting your history again. And right. Yeah, so I'll have to skip and go to the overview of the proof. Right. Yeah, so this is the overview of the proof. You have the escape algorithm that tells you that every time you hit a small unexplored region, you have a non-negligible chance of escaping and never of escaping far. And you use that in order to show that you don't create large blocks. And this is just what we proved in the escape algorithm. Every time you're inside the block, you have a non-negligible chance of escaping far and never returning, which means that the blocks will not be heavy. And then you combine this with a certain multi-scale scheme, like I just explained, to show that you have many relaxed times. These are times from which you have a positive probability of never hitting your history. And this exactly allows you to concatenate independent shorter cyclic walks into a longer cyclic walk and prove the induction step. This is the overview of the proof. Are there any questions?
Thank you.
Is there a 0-1 law for the probability of seeing in finite?
Yeah, the event that you have an infinite cycle is a 0-1 event because it's independent of the finite block. So indeed, the probability that you have an infinite cycle somewhere is either 0 or 1, and this argument shows that the probability that the origin is in an infinite cycle is positive, which means that with probability 1 somewhere we should have an infinite cycle.
Does this also give you some scale estimates on the probability of the allowed finite cycle?
Yes. Yes, so remember one of the inductive assumptions is the right transition probability. The cyclic walk has the right transition probability. So in fact, you know that the probability that the origin is in a finite cycle is exactly beta to the minus d/2. Like the probability that the random walk will return at the right time to the origin. Right, and so in dimension 4, what fails is that you no longer have this property that the past will be disjoint from the future with positive probability, and you will get like logarithmic. In fact, in dimension 4, if you have two simple random walks of length n, then they will intersect. They will have logarithmically many intersections, and this is not a lot. So you can prove some lower bound of the cycle length, but you are worried of some kind of an explosion, like logarithmically many intersections. Each intersection shifts you a little bit, so logarithmic amount of intersection maybe create more and more intersection, and it's hard to analyze. And in dimension 3, you will have many intersections, so it's completely hopeless.
When the answer came in at the beginning of the seminar, you said that there was no one to these things. Well, it's still not very clear for me this because like it seems that like as you increase the time, you have more interchanges, and this would like be helpful to create insight.
Right, that's the intuition. So in calculation, for example, how do you prove that it's monotone? You can couple all of them together.
Yeah.
But here, if you have an infinite cycle, you can break and it suddenly creates finite cycle. So it's not right. So long cycles can break into small cycles and then merge into longer cycles again. But it's possible, like as you said, it sounds very reasonable that it is monotone. The probability that the origin is in an infinite cycle increases when you increase beta. But it's not clear. On trees, it is known that you have the result. So Omer proved that on trees with large degrees, you see infinite cycles when you run it for a sufficiently long time. Then Ellen Hammond proved it and showed that like for smaller degrees you have infinite cycles, and then he had another paper showing that you also have the critical time on trees with sufficiently high degree. So on trees, it is known that you have a critical time. Before the critical time, you have finite cycles. After, you have infinite. But on ZD, it's still open. I think other lattices should work. You need some. So here we use the Brownian. We coupled it with the Brownian motion, so you need to have the notion of Brownian motion. But it's possible that you can extend it for other graphs with polynomial growth or some other assumption. It's worth trying.
What would be the coupling with Brownian motion?
That's right. So, yeah. Are there any other questions?
So let's thank Dor